Algorithm. Now, can you define it? Many people use this word every day, but very few can define it correctly. By the end of this video, we will cover the 5 properties, work through one full example, and look at the 5 big questions the field asks. Data structures and algorithms foundations. What is an algorithm? Here's the test. 3 of the next 4 instructions are algorithms. 1 is not. Watch for the difference. A. Multiply every number in a list by 2. B. Pick the biggest, or maybe the second biggest, from a list. C. Find the shortest path between 2 cities. D. Reverse a string character by character. Pause the video and answer for yourself which one and why. We will come back to the answer later in this video. An algorithm must be seen to be believed, Donald Knuth. So we will not only define it, we will also see one step by step. The definition, an algorithm, is a finite sequence of steps with 5 strict properties. 1. Definiteness. Every step is clear and exact. There is no room for do this or maybe do that. 2. Effectiveness. Every step is something you could do by hand using just pencil and paper. 3. Finiteness. It terminates, it stops. 4. Input. The algorithm takes 0 or more values from outside. 5. Output. 1 or more results. Definite, effective, finite, input, output. Memorize those 5. Let's see one. Euclid's algorithm from around 300 BC. Older than algebra, older than the printing press. The problem, find the largest number that divides both A and B evenly. We call that the greatest common divisor, GCD. Here it is. 3 lines, while B is not 0. Replace A and B with B and A mod B. When B hits 0, return A. That's the entire algorithm. 3 lines, 2300 years old. And still, to this day, the optimal way to do it. Let's trace it. We'll compute GCD of 48 and 18. Step 1, A is 48, B is 18. 48 mod 18 is 12. Step 2, now A is 18, B is 12. 18 mod 12 is 6. Step 3, now A is 12, B is 6. 12 mod 6 is 0. B is 0. We stop, return A. The answer is 6. GCD of 48 and 18 is 6. 3 iterations, that's it. A small note for beginners. Take pencil and paper, or even slate and chalk, and run the algorithm yourself, step by step, by hand. That is what makes a concept stick. Without this practice, it feels like you have learned the idea, but it slips away the moment the video ends. So pause now and trace Euclid for any 2 numbers of your own. Now let's check Euclid against the 5 properties, one by one. Definiteness, check. Mod is mathematically defined. Same input always produces the same output. No ambiguity. Effectiveness, check. You just watched it run on a slide. Pencil and paper. No supercomputer needed. Finiteness, check. Every step B gets strictly smaller. It can't shrink forever. It hits 0. Always input, check. 2 integers, A and B. Output, check. 1 integer, the GCD. 5 for 5. That formally is an algorithm. But how do we actually prove an algorithm terminates? For Euclid, it is easy. The value of B is a non-negative integer, and it gets strictly smaller every step. A strictly decreasing sequence of non-negative integers cannot go below 0, so it must reach 0 in finite time. That is the proof. Euclid's algorithm always terminates. But what about an arbitrary piece of code? Some loop, some recursion, written by someone else. How can we be sure it ever stops? In 1936, Alan Turing proved a remarkable result. There is no algorithm, no general procedure that can decide for an arbitrary piece of code and an arbitrary input whether it will halt. This is called the halting problem, and it is provably undecidable. This is why finiteness is a real property to check. We have to prove it case by case, like we did for Euclid. There is no general shortcut. Every algorithm has to come with its own argument for why it terminates. Now the counterexamples. Three things that look algorithm-shaped but aren't. Add 6 or 7 to X. Which one? The instruction doesn't say. It fails definiteness. It's not an algorithm. Run forever, handle requests as they arrive. This is what an operating system does. It works, but it never stops. It fails finiteness. We call this a computational procedure, not an algorithm. Solve chess. Try every possible move. This one is tricky. It is correct. It does terminate, but it takes roughly 10 to the power 120 moves. The universe is only 10 to the power 17 seconds old. Correctness alone is not enough. An algorithm must also finish in a reasonable amount of time. Let's go back to the 4 options from the start. You had 10 seconds. Now let's see which is which and why. A. Multiply every number in a list by 2. This is an algorithm. Every step is defined. The loop terminates when the list ends. Input and output are both clear. Check. B. Pick the biggest, or maybe the second biggest, from a list. This is not an algorithm. The phrase "or maybe" is the problem. The instruction doesn't say what to do. It fails definiteness. This is the one. C. Find the shortest path between 2 cities. Yes, this is an algorithm. It is a well-defined problem. Known algorithms solve it. Dijkstra's algorithm and A*. Both give the same correct answer every time. D. Reverse a string, character by character, an algorithm. Character by character is literally the procedure. Definite finite. Done, eh? Now let us step back. Every algorithm's textbook and every research paper is really asking 5 questions. Question 1. Design. How do we build an algorithm? We use pattern-based strategies, divide and conquer, greedy methods, dynamic programming, and backtracking. These are the reusable toolkits. We will cover them later in this series. Question 2. Express. How do we write an algorithm down so that our exact intention reaches the code? Euclid wrote his in 3 lines. That is a very good answer. Question 3. Prove. How do we know an algorithm is correct? Not by testing alone. We use a mathematical property called an invariant, something that stays true at every step. For Euclid, GCD of A and B is equal to GCD of B and a mod B. This equation holds at every step of the loop. That is the proof. Question 4. Analyze. What do they cost? Euclid runs in O of log n steps. Best, worst, and average case. This is where big O comes from, coming in future episodes in this playlist. Question 5. Test. Debugging finds bugs. Profiling finds where the time actually goes. 2 different tools, 2 different jobs. So which of these 5 questions matter the most? The answer is 2 of them, design and analyze. Design separates a programmer who just solves a problem from one who solves it well. Analyze tells you whether your code will scale or whether it will collapse as soon as the input becomes large. And analyze needs a language of its own. That language is Big O, coming in future episodes in this playlist. The best programs are written so that computing machines can perform them quickly and so that human beings can understand them clearly. Donald Knuth. That's the standard. Both halves. Thanks for watching. If this video helped you, please like, subscribe, and leave a comment below. Tell me which property was the most surprising for you. More on algorithms, analysis, and Big O is coming in future episodes in this playlist. See you there.